Consider the physical mass of a modern container ship. These vessels operate like floating cities, carrying up to 18,000 individual containers on a single voyage. Every container placement must respect the ship's structural stress limits, the exact sequence of its destination ports, and its final seaworthiness. This creates what computer scientists call an NP-complete problem. An NP-complete problem is a computational puzzle so complex that finding the absolute perfect arrangement is impossible for a human mind to solve in a reasonable time frame. When crews are forced to rely on manual planning or basic heuristics to solve it, the result is an inefficient stowage plan. The ship sails with dangerous weight imbalances, massive empty voids of wasted cargo space, and thousands of containers that must be repeatedly moved out of the way to reach other cargo underneath. Wasted space and excess weight dictate that these ships burn millions of tons of heavy fuel oil unnecessarily. That physical inefficiency clashes directly with the International Maritime Organization, the United Nations agency responsible for regulating shipping, and their strict mandate for the industry to reach net zero greenhouse gas emissions by 2050. Meeting these targets requires the shipping industry to transition into a mathematical operation where every voyage is treated as a solved computational problem. That optimization begins long before a ship ever touches the water. Shipbuilders like HD Hyundai are moving construction from the physical slipway into the digital realm, partnering with software platforms like Siemens Accelerator. They are building a digital twin. A digital twin is an exact, interactive data model of a physical asset, constructed entirely within a virtual environment before a single piece of real steel is ever cut. Inside this virtual shipyard, engineers use AI trained on synthetic data to simulate extreme ocean conditions. They push the virtual hull to its breaking point, testing structural integrity and physics against hurricanes and massive swells. By solving for stress fractures and engineering failures in the software first, the industry eliminates the material waste and financial risk associated with real-world trial and error. Once the digital hull is perfected, the next challenge is filling the empty cargo bay. To solve this NP-complete loading puzzle, planners use multi-objective linear programming, evaluating thousands of variables simultaneously. This 3D grid represents the ship's exact cargo architecture. Evaluating millions of configurations simultaneously, the algorithm tests each block against structural limits and route sequences. In under 10 minutes, it generates a perfectly optimized master stowage plan, distributing weight and minimizing quake rain movements. These mathematical optimizations continue once the vessel sets sail, moving from the cargo bay up to the bridge. Systems like Abacus Hynos act as an AI-driven Level 2 autonomous navigation assistant. Hynos integrates camera vision with AIS and ARPA, which are automated tracking systems that identify other nearby ships and radar targets to safely guide the massive vessel. When weather degrades, the system pulls data from infrared sensors, allowing the AI to see through the fog or darkness. It constantly calculates the optimal route, making micro-adjustments to the rudder and engine RPM without human hesitation. Marrying a mathematically flawless cargo layout with an autonomous navigation system creates a continuous loop of efficiency that reduces fuel consumption across every nautical mile. To see the real-world impact of that efficiency, you have to look beyond a single ship and view places like the Indonesian archipelago, a geographically fragmented nation made up of over 17,000 individual islands. For these dispersed island populations, highly efficient sea freight functions as the non-negotiable physical infrastructure of daily life. Keeping millions of island residents supplied requires moving a staggering volume of cargo through active terminals. Any logistical friction or wasted space in this network increases the cost and difficulty of distribution. When digital stowage planning and autonomous navigation are deployed across an entire fleet, the results compound. The network operates with higher density, effectively eliminating empty cargo space and logistical dead ends. By maximizing cargo density and minimizing fuel waste in transit, these algorithms directly lower transport costs. This efficiency ensures that basic consumer goods remain accessible for the people living on those islands. This synchronized algorithmic efficiency provides a scalable path toward hitting global net zero targets, reducing the carbon footprint of the very transport networks these islands depend on. Solving the multivariable equation of a container ship stabilizes regional supply chains, providing the mathematical framework for a more efficient, lower-carbon global trade network.